I want to cover a range of topics that are current topics around the use of computers in safety-related and safety-critical applications. I want to talk about what actually causes accidents. What do we mean when we say that something causes an accident? About the way in which safety engineering has developed over the years. The social question of how safe is safe enough. And that leads into the technical issue of what can you actually learn from experience? How reliable is something that has run without failing for a year? What can you actually say about it on the basis of simply the experience that something has worked without failing for a year, let's say, rounded up to 10,000 hours? And then I want to look at the current international standards for safety critical systems, very, very briefly, and make a few critical comments, particularly about the implications of cybersecurity issues, which of course we've covered in previous lectures. We see software in lots of different areas now that are safety critical and safety related. From the low risk areas, the temperature control on something like a tumble dryer, for example, or the cutouts that are on tumble dryers, which of course have been causing houses to burn down recently and have led to a recall of a major manufacturer's tumble dryers, as you probably read. Through to the really critical things, like the computers that actually control the interlocking between signals and points on the railway line to make sure that the signals don't signal that it's safe for a train to proceed when actually the points are set to divert a train into the path of another train. They're highly safety critical, of course. So we talk about safety related for the low risk, safety critical for the high risk areas. There's a lot of blurring between the two sets of terminology. What causes an accident? Here's a completely fantasy accident. Imagine a car. A motorist is driving a new sports car to an important meeting. The simple facts are that they skid on a patch of oil on a corner and hit a road sign. Now, what would you say was the cause of that accident? If it was the speed, how far back do you go for why the driver was driving so fast? Was it because they were late for a meeting? Was it because they'd been... Well, why were they late? Was it because they overslept because they'd been kept up all night by their baby screaming? If it was the oil, imagine that the oil was there because of a leak in the gearbox of a preceding lorry, and that the leak in the gearbox was perhaps caused by the lorry hitting a pothole that hadn't been maintained by the local authority in the road that they were driving over. Or that it was caused by bad maintenance of the lorry, and that had led to the leak and therefore to the oil. The issue is, major accidents, most accidents, don't actually have a single cause. Usually for something serious to go wrong, lots of different things have to go wrong simultaneously. And somehow, safety engineering has got to address all these issues to try to make sure that the system, in its final use, in the circumstances where it's going to be deployed, is actually adequately safe, whatever we mean by adequately safe. And we'll come back to these issues later. Software is taking more and more of the responsibilities that previously perhaps would have been taken by humans. And under these circumstances, a lot of these issues of what is the cause, what do you need to do in order to reduce the probability of error occurring, end up embedded in the software and become the province of the software engineer and the systems engineer of the system that contains software. So we end up with software issues, the sorts of things that we've been talking about over the last 8 or 9 lectures, coming into this area where there is serious potential risk to human life, to injury, to significant damage to the environment, and so on. Now, safety engineering really grew out of the process industries, and that looks reasonably complex. It's just a bit of a refinery, but they're relatively simple systems compared with a significant software system. You know, a set of pipes and valves, reactor vessels, relays, temperature gauges, some level of control, which increasingly now will be software control, but could just be a manual control room, somebody looking at the various alerts, the various gauges, reacting to the alarms, and so on. The sort of failures that you get in these systems are typically physical failures, almost always physical failures, stuck valves, stuck relays, corroded pipes. There's a particular problem in the offshore oil industry at the moment because the wraps that are used around pipes are leading to corrosion underneath the pipes, and there's a major issue there that is gradually being resolved, and trying to work out exactly how to handle that effectively. These simple systems, relatively simple systems, led to the disciplines that are at the heart of traditional safety engineering. And the safety analysis, because you were looking typically at physical failures, focused very much on the reliability of individual components. So it became the job of the engineer to determine how reliable particular components needed to be, and therefore whether they needed to be replicated to provide resilience, or whether you needed to buy particularly high spec relays or valves or whatever in order to achieve the safety goals that you required. And so you would start with a top-down analysis of what could possibly go wrong, and then what series of component failures could lead to that top-level condition of something going wrong and potentially, therefore, causing an accident. And we talk about faults and failures. The fault is the abnormal condition that may lead to a failure. The failure is the inability of a system or a subsystem to carry out the function that was intended. And a failure, as we have seen from that spurious story about the car accident, can be the consequence of one or many faults, and typically, actually, in modern systems that have been reasonably well engineered, it will be more than one fault before an accident occurs. Not always, by any means. And you can do fault tree analysis top-down. You can do failure modes and effects analysis. Once you've got your system design, you can do a bottom-up analysis to say, what would happen if these components failed? What are the consequences of these components failing? And you can do the bottom-up analysis as well. And this, between them, this set of techniques, and there are more, for doing hazard analysis, enables you to identify what you need to do in order to protect your system, to put in place the safety functions that will keep the system from failing, even in the presence of faults. And it's important to point out that a system can be safe, even if it's unreliable, because any system that can fail safe is likely to be safe having failed into a safe mode. If your car won't start, you're not going to have a car accident. You might have a heart attack, but you're not going to have a car accident. So your car can get safer and safer the more and more unreliable it gets. There is a tension here. And it can easily cause confusion, because at some level, when you have built a system where you have identified particular safety functions that are actually managing the behavior of the system in the face of particular faults occurring, then the reliability of those safety functions is, of course, a safety issue. So you end up looking at safety through the eyes of reliability and the probability of failure of particular systems and subsystems within your overall safety critical system. Now, the safety engineer being an engineer, doesn't want to over-engineer. And in any case, in many organisations, when a system has been designed, there will be somebody who comes through to try to do some value engineering on it. In other words, to try to reduce the cost of the design before it's actually built. And so there is an analysis that has to be done of how safe is safe enough in this environment. And these are social questions. What probability of failure should we permit? How probable are we going to allow the protection function in a nuclear reactor? How high can we permit the probability to be that protection function will fail when it's called upon to shut down the reactor because something is going wrong? And there are, as we shall see, industry figures, recommendations or standards, some of them firm regulations, for what those probabilities of failure are permitted to be. But they are social questions. And as we shall see in a minute, the answers that come out are not necessarily the same in different application areas. And sometimes it's quite hard to see any logic between the figures that get used in one application area and the figures that get used in another. And how much should we spend to avoid or reduce by one the probability of failure accident on the railways or on the roads? This was a significant issue in the aftermath of the Hatfield rail crash, for example, when the rail cracking that was determined to be one of the causes of that accident led to the railways being essentially shut down, and certainly very significant reductions in service in terms of reducing the speeds and indeed closing sections of track until the inspection and corrections could be done. The consequence of which was, of course, that more people used the roads. And the probability of an accident on the roads being much higher, a fatal accident on the roads being much higher than on the railway, statistically you can be confident that the decision to do that on the railways did in fact increase the number of deaths that occurred rather than decrease it, which is what you would have hoped the response to an accident would have been. But these are social and political issues. It would not have been politically acceptable to have another accident with the same primary cause. And therefore, the political decision has to be taken that we're going to do something which logically is perhaps the wrong thing to do. And we will see, too, that you only have to look at the figures in different government departments. The level of investment that is put in to save a life on the railways is much higher than the investment that is put in to save a life on the roads. The cost of re-signalling or of putting in automatic train protection, for example, would undoubtedly save more lives if it was spent buying kidney machines or doing work on the roads to address some of the more dangerous corners. You know, there are accident black spots, and which ones actually get sorted out in any given year or decade depends on budgetary constraints. Difficult social challenges, which then the safety engineers have to deal with and to live within. And you can do the calculations on the basis of what does get done, where the investment gets placed. It's possible to do calculations that actually put a value on the implied value of a life. And it's called in the trade the value of a statistical life, and you can do this back calculation. And it's defined, as you can see, as the additional cost that individuals would be willing to bear for improvements in safety that in the aggregate reduce the expected number of fatalities by 1. You might think, it's open for discussion, perhaps we'll discuss it at the end of the lecture, whether the NHS and the Department of Transport ought to be using the same value. Whether it ought to be common, certainly across, within a country, should it be the same internationally even? They're not the same internationally, and this is a selection that have been published. There's all the references for the things that I'm talking about you'll find in the transcript as usual, and indeed for a lot of things that I won't get around to mentioning. These are some figures that have been published in millions of US dollars at year 2000 value, in order to try to sort out the inflation issues that you get when you're doing these measurements at different times. And as you can see, it varies fairly dramatically from $7 million in the USA to 9.7 in Japan, to less than $1 million in Taiwan, to just a bit under 2 million in Hong Kong, and so on. And actually, the calculations, I guess, are quite tricky to do, because you have to make a lot of assumptions. So if you go searching on the internet, you'll find various websites that say that they are listing the value of a statistical life, and they won't all be exactly these numbers. They'll be different. But the general message, I think, is clear, that there isn't a consistency in the value that is placed on a life if you work it out backwards from where countries choose to spend their money to save a life. Now, in Great Britain, the overarching safety regime was set up after the Lord Robins report in 1974 by the Health and Safety at Work Act. And that is a risk-based approach to safety. The intention is that it should be proportionate to the risk, that it is as bad to over-engineer for safety reasons as it is to under-engineer for safety reasons, that the regulator should not dictate how something should be done, because technology changes. There are always better or different ways of achieving the same end. And in any case, you mustn't take the responsibility away from the person who ought to be controlling a particular safety risk. So the underlying philosophy of the Health and Safety at Work Act is that people who create a risk have a duty to reduce it as low as is reasonably practicable. And that leaves the duty with the person who's created the risk, and enables them to argue about proportionality, about what is reasonably practicable in order to manage this risk. And there are two general duties. I've coupled them together here with the bold "and" in the middle. The first is in Section 2 of the Act, and is the duty of employers to ensure the health and safety of their employees, and the Section 3 duty, which is the duty of employers to ensure that people not in their employment do not suffer risks to their health and safety as a consequence of that employment, of that business activity. These are strong requirements. And there are a number of regulators that regulate under the Health and Safety at Work Act. Health and Safety Executive is the primary and overarching one, but in shops and offices, for example, it's the local authorities that are the statutory regulator. On the roads, it's the Office of on the rail, it's the Office of Rail Regulation. The Office of Nuclear Regulation is the regulator for the nuclear industry, and so on. There are a few. Food Standards Agency carries out the work in the food area, and so on. But for the vast majority of significant hazardous sites, the construction industry, farms, places like Alton Towers, power stations like Didcot, it's the Health and Safety Executive that is the regulator. And there are, of course, an awful lot of accidents that still occur, and the courts are increasingly severe on people who have failed in their duties. We're starting to see fines that are £500,000 or £1 million on big organisations. And in fact, last week, somebody was sent to prison for 2 years for quite clearly failing in their duties in a construction collapse that led to the death of 2 workers. So these are serious requirements. But as we will see, not very well followed generally through the software industry. This is just something that it's worth looking at in the transcript, really. The term, so far as is reasonably practicable, has actually been defined in the courts, and it's been defined as there is a presumption that the duty holder, the employer, will in fact put in place the necessary safety protections to manage whatever risks they're creating. If the duty holder wishes to argue that they don't need to do that, then the burden of proof is on them to argue that the cost of doing that would be grossly disproportionate to the degree to which the risk is reduced. And that's the balance. The presumption is that you'll do it, but you don't have to do it if the benefit if the cost would be grossly disproportionate to the benefit. And it's up to the duty holder to make that argument. And there's a chunk of text below there that it actually explains the HSE's approach to this. And there's really, really good guidance on the HSE website. Again, I've given some references to it. In fact, this is taken from the main HSE document on managing safety and on reducing risk. And it shows this tolerability of risk where at the bottom of the triangle you've got a broadly acceptable region, very low risks. The particular hazard is not high. You know, the biggest risk to your employees is that half a dozen people might bruise their knees. Clearly not worth investing a large amount of money in ensuring that doesn't happen. At the top, there are unacceptable risks where the risk reduction simply can't be done, and you mustn't therefore continue with that business activity. It has to be stopped until it can be redesigned in a way that actually brings it down into the tolerable region between the two extremes. And then in the tolerable region, your obligation is to reduce that risk as far as is reasonably practicable. This has proved to be an extremely successful approach, this risk-based approach that leaves the duty with the duty holders rather than a prescriptive approach that tells them how to manage a risk, has proved very successful. The UK has got one of the best health and safety records in the world, and more countries are actually coming to the UK to ask for guidance in how to set up a safety management regime that follows this risk-based and proportionate and duty holder approach. So it's internationally recognised as a very successful way of working. We talk about hazards, anything that causes harm. So hazard analysis is looking for the hazards. What could possibly go wrong? And many industries have got fairly well-developed and experienced-based ways of looking for these things. The chemical industry will run a set of keywords against a particular situation, you know, too hot, too cold, too quick, too slow, too high pressure, too low pressure, in order to sort of test whether there are conditions here that could occur and could then lead to a need to do further analysis. The risk is a combination of probability that a fault that the hazard will actually lead to an accident, and the consequences of that accident. So it's the multiplier of those, it's the product of those two things. And then, as we've seen, for each hazard you assess the risk, and then your duty is to reduce it to make it as low as is reasonably practicable. And we talk about the ALARP principle, the as low as reasonably practicable principle. And in particular industries, aviation has a requirement that catastrophic failures must be extremely improbable, in the language of the regulations, of the standards and guidance. And that's interpreted as a probability of catastrophic failure of 10 to the minus 9 per hour, once in a billion hours of operation. The nuclear industry has this statement that reliability claims for a single software-based system important to safety of lower than 10 to the minus 4 probability of failure on demand or probability of failure per year shall be treated with extreme caution. They are basically saying don't put claims that you've managed to achieve a lower failure probability than that into any safety case that you submit to us, because you're probably not going to get it approved if you do. And that's good news, but not exactly the same as the aviation standards. And the difficulty with all these claims that you would need to make and to justify in a safety case is, what evidence are you going to base the safety argument on? How are you going to produce evidence that you've reduced the probability of a catastrophic failure in an aircraft or in a fundamental critical system in an aircraft to 10 to the minus 9 per hour? Now, the sort of failures that we were talking about in the process industries tend to be these sort of physical failures. You get corrosion, you get pipes bursting, you get wires coming off. And so a lot of the thinking by safety engineers, a lot of the work that has been done in producing standards has at its heart a mental model, or even an explicit model, that is about physical failures. And these are random failures. They occur as a result of a physical process that takes a certain amount of time or in response to a certain amount of stress. And so they're considered to be random failures. Software failures are not, in that sense, random failures, because where there is a fault, a design fault in some software that with the right or with the wrong inputs causes that software to fail, it will always do so. Whenever those circumstances arise, the software will fail. And so software failures are regarded as systematic. They're design failures. And if you look back at all the literature for the safety engineering of process plants in the 1980s, of low complexity electronic circuitry in the 1980s, and so on, systematic failures in those systems were essentially ignored. The assumption was that your design processes would be good enough to make sure there weren't any, and that therefore all you had to do was to worry about the random failures caused by the fact that your components would wear out or a wire would break. And of course that approach doesn't work for software. I remember going to conferences back in the 1980s where people were having serious conversations about what is the probability of failure of an assignment statement, and should we find another way of implementing the functionality of an assignment statement, not using assignment statements because they fail. Can we do it? And it's just nonsense. You know, it doesn't make any sense to be thinking about software that way. And so actually in those early conferences, when anybody mentioned software reliability, everybody laughed. And software safety was considered to be just a complete nonsense subject. And of course, software-based systems are very complex. You know, we've got 100 million lines of software in a modern car. The failures are systematic, but the triggering conditions arise randomly because the software system is operating in a world where a lot of different things are affecting the inputs to that software, and those things are essentially occurring at random. So we have a lot of uncertainty about the probability of the conditions arising that will cause software to fail. We have two types of uncertainty. We have epistemic uncertainty, an uncertainty of knowledge because we don't fully understand the complex system, and therefore we don't know whether a particular set of circumstances will cause the system to fail. And we have aleatoric uncertainty, which is the uncertainty of the randomness of the arrival of the particular set of circumstances that are going to affect the behavior of the software. The fact that the world is a random place, weather conditions are random, the behavior of all the things that influence software quite often will trace back to random causes. How do we reason about uncertainty? We've got these two causes of uncertainty. Well, the algebra that we use for reasoning about uncertainty is probability. And so you do get probabilistic analyses of software. There's a lot of work that has been done on the probability of failure of software, and it's a perfectly reasonable thing to be doing, as you can see from this line of reasoning. Astonishingly, it's still controversial. Even within the last month, on the professional mailing lists that discuss deep technical issues of software safety, relating to aircraft, relating to driverless cars and so on, there will be major arguments where people are still arguing that it makes no sense at all to talk about the probability of failure of software. So the industry hasn't matured to the point where across all the different application domains, even in areas that are safety critical, where you might think that the engineering was at its peak, it still hasn't matured to the point where people really understand the underlying science and the mathematics that is the way in which the engineers need to be able to work with these probabilities of failure. Now, as we've seen over a number of lectures, the primary way in which software developers gain confidence in their software is by testing it. So it becomes a very important issue. What can we actually learn from testing software? And we know that we can't make strong claims on the basis that we haven't found any faults. We can't claim that there are no faults in the software because testing only shows the presence, not the absence of faults. We know that. That's fundamental. But let's look at what claims could we make about a system that has never failed over some period of time. Because arguments are used on the basis of, oh, well, this is proven in use. It's been running for this length of time. It's safe. We can use that in a safety argument in our system. So we'll come back to what strong assumptions we need to make in just a moment. What's the probability of failing per hour of a program that's run for, let's say, 10,000 hours without failing? If you do the stats on the basis of, as I say, 2 or 3 strong assumptions, and it doesn't actually matter much which of the statistical distributions you choose to use, the answers come out sufficiently close that you end up with these sorts of numbers that are close enough for engineering purposes. The probability of failing per hour, if it hasn't failed for 10,000 hours, is 50% that it won't fail in the next 10,000 hours. Just 50%. So you can make a claim, but that's the limits under some strong assumptions. If you need 99% confidence, if you need to be significantly more confident than just 50% that it's not going to fail in the next 10,000 hours, in the next year, then that requirement goes up to 46,000 hours. And you can use that as a sort of general rule of thumb, that if you're looking for a probability of failure of 10 to the minus n, then if you only need 50% confidence you've achieved it, then 10 to the n hours of fault-free operation will give you that confidence. If you need 99% confidence, then it's 4.6 times 10 to the n hours that you need. And that works pretty well, and you'll find in the paper that I've referenced, which is written by Professor Bev Littlewood and one of his colleagues, one of our leading statisticians in this area. You'll find a reference to that in the transcript, and it was a paper that was done in order to justify the way in which the shutdown system for the sizable B nuclear reactor was being validated. And it's a published and well-referenced paper. So that's what we get out of the statistical analysis. But the assumptions are very strong. And the first is that the operating conditions in the future have got to be identical to the ones that have provided you with the evidence that you're relying on. And that means you can't legitimately transfer experience from one context to another without being able to reason very, very strongly that the difference in the 2 applications or the 2 contexts is irrelevant to the failure probability. And that's a really, really onerous requirement. And this is the Ariane 5 rocket, which went wrong because it self-destructed, because the protection system was the Ariane 4 protection system, and the circumstance, and in fact there was nothing wrong with the rocket. It was just that the operating conditions were different from those that the protection system had been led to expect were legitimate, and consequently it blew the rocket up when in fact it would have been safe to let it continue. Second obligation is that you do actually need to know whether it's failed or not in your 10,000 hours or however long of previous experience. So you need to be confident that you have managed to detect all unsafe failures, and that you've got evidence that you've done that, and that you have collected the logs and analysed them and so on. So auditable evidence becomes essential. And the third one, and perhaps the worst for practical purposes, is you mustn't change the software. In fact, if you do these sort of analyses, you realise that if you're dealing with highly reliable systems that have been demonstrated to be highly reliable, and a fault occurs, it's a serious mistake to fix it. Because the calculation, you have to go back to do your complete revalidation if you do. I mean, clearly, if you're using mathematical proofs and you can show that the change that you're making hasn't invalidated the proofs, then you're home and dry. But if you're relying on evidence from testing, if you're relying on statistical evidence and you change the system, it's a new system. You're going to have to gather that evidence again, unless you can reason about the change that you've made and show that it could not have affected the historic evidence, which typically, if you're not using mathematically formal methods and you're relying on testing, you can't do, obviously. So, because you won't have the formal structures to do that reasoning. And the reason why it's a mistake to fix the fault is that actually the amount of evidence you need in order to show a probability of failure of 10 to the minus n for a system that has failed, let us say, exactly twice in that period, isn't very many more hours than for a system that has failed once or not at all. Having a very small number of failures in a relatively long period of time doesn't damage your statistical reliability very highly. So actually, you can make a better safety case by not fixing those errors that occur, if there are very few of them. The consequence of this, though, is that almost all the safety cases that contain any argument based on proven in use, we're using this component because it has worked successfully, or this subsystem because it has worked successfully in previous systems, they're invalid. They're simply not sustainable as logically valid safety arguments, and yet you see them everywhere, and you're even permitted to do it by some of the international standards. Now, the implications of these calculations are that you need an awful lot of evidence for safety certification if you're going to try to certify something to very low probabilities of failure. And so various other ideas have been put forward as to how you get around it. And one that is quite prevalent is the notion of inversion programming. It's the equivalent of the hardware technique of having multiple hardware subsystems which are backing each other up. And the idea is that you write the software, let's say 3 times, completely independently. You argue that means that they're going to fail completely independently. And so you feed the inputs into all 3 of the versions, and you have a voting system that combines the outputs and decides on the basis of a majority vote what the right output should be. Now, that assumes that the systems fail independently, and there have been some classic experiments by Knight and Leveson that shows that they don't, and that's for pretty obvious reasons. Even completely independent teams will typically, firstly, be using the same specification, and so if there are faults in the specification, they'll show up in all versions. They will make a number of the same assumptions about the operating environment. They will probably draw on common libraries of software. They'll probably draw on common approaches to doing software development based on their background, on their previous experience, and so on. And of course, they will make mistakes most likely in the most complex part of the program. And therefore, actually, what you get is nothing like independent failure. This was a highly controversial paper because it really undermined a lot of what industry was doing, and it got robustly criticised in the peer-reviewed literature. And Knight and Leveson have robustly responded to those criticisms, and it makes a good read. And I recommend the references that I've given you there. It's worth following them up. But the take-home message is inversion programming actually doesn't solve your problem. And the idea, of course, was that you could then combine 3 10 to the minus 3 systems to get 1 10 to the minus 9 system. I should have said that earlier. And of course, for those reasons, it doesn't work. What the international standards do, 61508 is the big safety standard. It's an IEC, international standard, and it's the one from which a lot of the other specific application standards are drawn. The standard for motor vehicles, for example, is drawn directly from 61508. And DO178 is the avionics standard, the standard for safety-related systems in aircraft. And they assign system integrity levels, which are essentially based on how reliable you need your safety functions to be. And then, based on the integrity level that has been assigned, they give you recommendations on the development methods you should use. Whether you should write a formal specification, a mathematically formal specification, whether you should use structured methods, whether your programming language should have particular characteristics, and so on. And the underlying assumption is that the quality of the software that is produced is very closely related to the development methods that you use for producing it. Now, there's no empirical evidence that that's true. And there are very good reasons for believing that it wouldn't be. There's obviously going to be some level of relationship. I mean, the fact that you are following a rigorous engineering set of methods is obviously going to be good news, but it's perfectly possible to write bad software using good methods. That's pretty straightforward. And the recommendations that are made are consequently they're illogical and they're unscientific. And this is the system integrity levels from IEC 61508, as I say, the big important European and international safety standard. And for the most important, the SIL 4, where you're looking for a probability of dangerous failure per hour that is up around the 10 to the minus 8, 10 to the minus 9 probability of failure per hour, dangerous failure per hour, there are strong, highly recommended practices. The lowest one that they care about, the highest probability of failure at SIL 1, you're still talking about a probability of failure which is between 10 to the minus 5, 10 to the minus 6 per hour, so less often than once a year. So the assumption is that if you're actually looking at something where the requirement is that it should only fail, let's say, once every 100,000 hours, no, if you're looking at something which should only fail, let's say, once every 6 months, then actually you don't even get onto this table. And ordinary industrial software development processes are considered to be adequate. Well, that's obviously absurd. But given that we can't show even that the highly recommended development practices that are highly recommended at SIL 4 can be guaranteed to produce a system that is at least as good as SIL 1, and we can't show that because the causal relationship just isn't there, how can you possibly justify these factor of 10 steps in between? The claim that having got to SIL 1, all you need to do is to add these extra 2 or 3 methods, move them from being recommended to being highly recommended, and you achieve the higher level of safety. It just doesn't make any sense. The whole structure of this standard, in my opinion, is flawed, and I've tried to change it and completely failed, because the maintenance process for these sort of standards requires that you you take a piece of the text and you propose a new piece of text that will fit into that point in the standard. I tried to radically revise the standard by doing that on one occasion. It took quite a long time, and they threw the whole thing out without addressing the fundamental issues. The maintenance team wouldn't wear it, and the standardization process is essentially broken in any case, because like most of these standards, they are captured by the people who go to the standards committees, and they are typically funded by industry, and industry doesn't want to be told to do things differently from the way they're doing it. So the standardization process is very difficult to get right at these sort of levels, where what you're asking people to do is to deliver something for which there can be no scientifically strong evidence. And that's a real challenge. The society has set the safety engineers a task for which there is no approach that can produce scientifically strong evidence that you've achieved a probability of failure up at the CIL 3, CIL 4 level. There just isn't. So that's the situation that we're in with building safety critical software. Now, the National Academy of Sciences in the US tackled this problem a few years ago and produced this report, Software for Dependable Systems. The examination question was, how should you go about building certifiably safe systems? I recommend the report. It's a good report. I should declare an interest. I was one of the editors of it. And the recommendations basically come down to three. The first is, don't make general claims about safety. Be very explicit about the actual properties that you're claiming. For example, this system cannot fail at runtime for any inputs that it can possibly encounter. This system cannot, this software cannot run out of storage. It cannot overflow. There will be no fixed point divides. Those sorts of properties can be claimed, and you can produce very strong evidence for them. The second thing is, having been explicit about what you're claiming, produce strong, scientifically sound, independently verifiable evidence to support the claim, and build it into a safety argument that says, here is the evidence, here is the reasoning, here are the conclusions that say that this is acceptable for use in its intended environment. And the third one is get the expertise right. You're going to need people who really understand the best software and systems safety engineering, but you're also going to need people who really understand the domain, because an awful lot of accidents, particularly the ones that get through and occur at the high levels, when people are really trying very hard and building systems that are designed to be extremely safe, they tend to be misunderstandings about the application domain. They tend to be wrong assumptions about the world. And unfortunately, the world has not supplied us with a formal specification for how it behaves. So we can't do the reasoning from here's a specification of the world, and therefore these are the assumptions we're building into our system. So you can't reason all the way through. There's always going to be that informal step between the requirements that you've got and the system requirements that you then impose on the system designers. Finally, what I wanted to say, there are a lot of safety critical systems in use. Many of them do seem to be fit for purpose. They're not demonstrably as safe as reasonably practicable, and that's an issue, and indeed can be a legal issue if and when they fail. But nevertheless, we have to accept that despite the fact that the development methods are essentially craft methods, that they are experience-based and people are trying very hard using very skilled people. The people who are building aircraft systems do an extraordinarily good job. And typically they get it right. If you look at the failure history of modern aircraft, they don't achieve the standards in the first few years in service, but by the time they've been in service for a while and a few of the errors have been fixed, then actually they are starting to achieve these 10 to the minus 9 per hour and better probabilities of failure. So industry is actually doing better than the standards and using better methods than the standards require in those really critical areas. That's typically the case. Safety cases are not good. That's an observation I would make. I've never yet seen one that I really believed. As I said earlier, there is really no prospect that it will ever be possible to provide scientifically sound evidence for a probability of failure per hour of less than about 10 to the minus 5. And therefore, asking for that is simply a category mistake. It's trying to solve the wrong problem. So somehow we need to move away from that and come up with a better set of objectives. And the worst thing is that the current standards almost completely ignore the cybersecurity threat. And that is a really serious issue, and it's one that is being addressed. There's a new guide coming out from the IEC, the standardization body, telling people who write safety standards what they ought to be taking account of by way of cybersecurity issues. And that guide is out for review at the moment, so that will be starting to have an effect on the maintenance of the safety standards over the next few years. And the Health and Safety Executive is bringing out guidance for its inspectors on how to inspect major hazard sites for the cybersecurity risks, as well as all the other things that are inspected against. And the existence of that guidance, which will be published later this year, will undoubtedly have an impact on the industry, because it will cause people to review themselves to make sure that they're not going to fall foul of the guidance that is being provided by the Health and Safety Executive. But this is work in progress, and the cybersecurity threat is not yet being properly addressed in a lot of sectors of society, as we saw in the cybersecurity lecture. So that's that.